Welcome to clickmyproject.com. Now we are going to see the product for algorithm and architecture of configurable joint detection and decoding for MIMO wireless communications with convolutional codes. Next we are going to see the abstract for our product. The product introduces a novel low complexity multiple input multiple output detector tailored for frequency division multiple access systems suitable for efficient hardware implementations. The proposed detector starts with an initial estimate of the transmit signal based on a minimum mean square error detector. Subsequently, it recognizes less reliable symbols for which more candidates in the constellation are browsed to improve the initial estimate. An efficient high-throughput VLSI architecture is also introduced, achieving a superior performance compared to the conventional MMSC detectors with less than 28% added complexity. The performance of the proposed design is close to the existing maximum likelihood post-detection processing scheme, while resulting in a significantly lower complexity. The proposed design for the 16 QAM scheme is fabricated in a 0.13 micrometer CMOS technology and fully tested, achieving a 1.332 Gbps throughput, reporting the first fabricated design for SCFDMA MIMO detectors to date. A software version of the proposed architecture is also introduced, which is customized for coder systems. The That Generation Partnership Project defined a long-term evolution to meet the requirements of the 4G wireless communication. LTE combines multiple input, multiple output technology with orthogonal frequency division multiple access technology in the downlink and single carrier frequency division multiple access in the uplink to achieve peak data rates of 300 Mbps. Several designs have been proposed for SFDMA MIMO detectors, among which the linear frequency domain equalizer receives, including the minimum mean square error and zero phasing, are often used due to their simplicity. Similar to the case of MIMO systems, successive interference cancellation and iterative techniques can be used to enhance the performance of the FDE receivers. However, these techniques introduce long delays due to their iterative nature. The maximum likelihood receiver, on the other hand, offers an optimal bit error rate performance, but it requires very high computational complexity, especially in the FDMA receivers. Considering the compromise between the BE or performance and the complexity, typically suboptimal methods are employed. In our product, a detection scheme is proposed for MIMO FDMA systems, which provides near optimal performance with a significant reduction in the complexity, especially for large constellation sizes. The proposed design is fabricated with the CMOS technology and fully tested. Next, we are going to see the flow diagram for our product. In order to provide higher data rates, wireless systems are adopting multiple configurations with spatial multiplexing to support parallel streams of wireless data. In order to enable reliable delivery of digital data over unreliable wireless channels, the sender encodes the data using an error-correcting code prior to transmission. The additional information or redundancy ordered by the code is used by the receiver. The receiver utilizes it to recover the original data. Error-correcting codes are widely used in MIMO wireless communications. The most commonly used error-correcting codes in modern systems are conventional codes, turbo codes, and low-density parity check codes. As a code technology in wireless communications, forward error correction coding has migrated from the basic 2G conventional block codes to more powerful 3G turbo codes and LDBC codes forecast for 4G systems. The number of transmit antennas and transmit streams is typically 2 or 4, but could be as many as 8 or 12 in future. The complexity of the detection and decoding algorithms can vary greatly depending on the number of antennas, modulation, and channel used in it. As MIMO detector is used to recover and detect the multiple transmitted antennas, soft output MIMO detection process significant challenges to the MIMO receiver design as the computational complexity increases exponentially with the number of the optimal soft decision detector, the maximum posterior detector will consume enormous computing power and require tremendous computational resources, which makes it unfeasible to be implemented in a practical MIMO receiver. As such, there is a great need for efficient MIMO algorithms to reduce the MIMO detection complexity. A channel decoder is used to process the soft information generated by the MIMO decoder and reconstruct the original error-free data. Among all those channel decoders, LDPC decoders and turbo decoders are the two of the most important decoders that are widely used in wireless communication systems. Two major challenges of the decoder design are high throughput and flexibility. To support multi-Gbps data rate, we need to develop efficient algorithms and architectures. To support multiple communication standards, we need to develop flexible decoding algorithms and architecture. Finally, we are going to see the output for our product. The output will be shown in the Xilinx software. We write the program in the VHDL code. Just click the MIMO design icon. The software will be opened with our corresponding code for our product. We have to simulate the main program. The product's input and output configurations will be shown in the vsim isim. We have to give the constants and the clock pulses to execute our program. In the clock option, we have to give the force clock, then leading edge value is 0, trailing edge value is 1, and the period for the clock is 1000 nanoseconds. Then we have to give the RST value as 1. This is for reset. Apply OK. Then we have to enable force constant. Then we have to give the value 1. Enter. Then we have to give the force constant for the STBC 1. We can press apply and then OK or enter. In this case I am giving enter. Then the first two value I am giving 1. Then CHT I am giving 1. Apply OK. In this process there are multiple inputs and multiple outputs. I am giving constant values for the inputs. The inputs will be 8 bits and the output will be in 5 bit with 3 sections. The input sections will be given the corresponding values and the output section will show the output with the 5 bits values. For CH4 we have to give the force constant, then the input values will be in 8 bits. For CH5 we have to right click, then we have to give the force constant. In the force constant window we have to click the force to value, then the inputs will be in 8 bits. For CHN6 we have to give the force constant, then the value will be in 8 bits. Right click on the CHNN7, then we have to give the first constant, and the input will be in the digital, that is 8 bits. The inputs will be shown in these icons so we can give first constant 1001. The inputs will be in the digital format. For in SG1 the input will be in 8 bits. Then again we have to give the digital values in 8 bits. For SG2 we have give the first constant, then the inputs will be in binary. For input SG3 we have to give the input in the digital formats with 8 bits. The outputs will be shown in OP1, OP2 and OP3. These three are 5 bits. Then click the run button. Initially the outputs in the OP1, OP2, OP3 will all be in zeros. Then again give the value for RST as 0. Then apply and then click on OK. Then again run. This time the output OP2 will be shown as 01111. The sum is designed to group output bits generated from VSF and to convert them to the corresponding modulation symbols. Then we are going to see the implementation for our product. For implementation we have to click the implementation icon, then view RTL schematic. In this process we can see the NOC architecture for our product. The main basics of this is to create the VLSI architecture with the icons. We have to click the create schematic icon, then the NOC architecture for our product will be created. Then we have to see the synthesis report. Synthesis report shows the memory and the space that require for our product. These are the spaces and the speed that requires for our product. We can view in the synthesis report.